Alrighty, so this is try number 2 to get the HPLC data workup video correct. We start with the file that you're going to need, and the 5 printouts are in HPLC data, right? And we're going to start with Anthony because he's the lucky victim here, right? And actually, rather than look at it here, you can just download these files, right, to your computer. And then I have them open in Acrobat here. And this is Anthony 1, for example. Looking at this guy, you can see that there are 2 copies of the chromatogram. One on top here, one on the bottom. This one is recorded at 275 nanometers. And this one is recorded at 230 nanometers. Now, the point of doing it at 2 wavelengths is so that we can get confidence in identifying which of these 2 peaks is caffeine and which is benzoic acid. And I happen to know that caffeine has an absorption at 275 that benzoic acid kind of lacks. It's a weak band out there. And then sort of the inverse is true between 275 and 230 for benzoic acid. It's weak at 275 and strong at 230. So that confirms here that this 4-minute peak is caffeine and this 7-minute peak is benzoic acid. Now, what you're going to have to do is make a choice about what wavelength you're going to use, right? So since in this first one the computer didn't identify this small peak for benzoic acid at 275, we can just go ahead and use the 230 nanometer data for the analysis of caffeine and benzoic acid in this case. So we're going to look at 230 nanometers, and we're going to first get this peak here for caffeine, which is retention time 4 minutes and area 169.4. That's the metric we need to use. So that being said, let's put this into Excel. So we're going to come here, we're going to type concentration, signal, 5, 10, and 20 ppm, I believe is what we used. And we got 169.0, I believe, 169.4 rather. Then we're going to go down to the 10-minute, then we're going to go down to the 10 ppm data, right? 10 ppm are in the file Anthony 2 here. And we're going to go to, again, 230 nanometers and retention time 4 minutes. The area here is 328.3. 328.3. And then lastly, we're going to get the 20 part per million data here. Again, this is Anthony, and the parts per million is indicated in the descriptor up in the top here. And we're going to go from 275 to 230, 4 minutes, and we're 637, basically 638.0 absorbance units right there, okay? So these are the calibration data, and I think we can put these guys here. Now we're going to get signals also from caffeine for the unknowns for the Coke. So those are going to be in number 4, and you can see the chromatogram here. at 275 and 230. There's the peak at 4 minutes. This is caffeine. This is benzoic acid. And these are other slightly more hydrophilic components of the Coke. So 3.998 minutes, 698.4 is our first. Oops, wait. No, that's 275. Sorry, we have to look at 230 and 4 minutes, and that area is 400.95. So it's 400.95, and we're going to go to the last one here, which is 230 nanometers. I believe 448.37. Let me just double check the. Yeah, see, this is 275. This is 230. It just carried over to this page, so it's 448.37. Okay, so that gives you an idea of some of the variability that we have in the signal levels there. So let's linest these data, and that means we're going to highlight a 1, 2 by 5, and we're going to type here equals linest, put in the y values and the x values for the calibration. We're going to go to true and true. Close the parentheses and type Shift Control Enter, and there we have it. This is the slope. This is the intercept. These are the relative uncertainties in those guys, and then this is an important value called SY that we're going to use later. So now let's do some interesting things here. Let's make some predictions here. And this is going to be equal to m times x plus b, right? That's how that guy works. And let's just, on the m value, let's hit F4. And on the b value, let's hit F4. And I'll show you why that is. That is because when we drag it down, we want it to continue to point to these two cells, but we want the target cell B2 to advance to B3 and B4. So these are predicted values here. Now let's predict the x values for these guys. This is going to be equal, open paren, y minus b divided by m. Right? Now m we're going to F4, and b we're going to F4 as well. Alright, now we should be able to drag this guy down, and this should work as well. Right? So it uses this value in these two, this uses this value in these two. Now let's just get the sig figs under control here a little bit. And then these guys too. And let's indicate that they are predicted by highlighting the cells in green. Oops, not the text color, the highlight. Highlight them in green rather. And then we can highlight these experimental data in, let's say, peach here. Those are the acquired data. This is the linest here. I'll just put like a thick outside borders on that to delineate it. And so now we have our sample concentrations here. So let's sort of make a table here. We call it sample concentration. This will simply be equal to that. Let's drag this guy down. And here I'm going to insert a symbol here, and we'll find the plus or minus symbol here and click insert, close, and drag this guy down. And now we've got something we can say. Now we need to calculate the uncertainty in this value here, right? This value here comes from a calibration curve, right? It's these data are used to calibrate, and then the coefficients are used to compute the concentrations. When you do this, you need to use a special magic sauce formula here, which is actually given in the lab manual, and here it is. So I completed the worksheet, and I wanted to go over some of the parts. Basically, there's a few steps once you get the sample concentration. Get the uncertainty, ppm per can, milligrams per can, then the confidence interval on that. So the uncertainty on the ppm injected is the same trick that we've played before. We use this formula from the lab notebook, and so that formula is equal to, it's this term, I just leave parentheses for that, times square root of another term, right? And this square root guy has 3 terms inside it, right? I'll go and fill in the terms. This is SY divided by M, right? M is positive, so we don't need the absolute values, right? Then this term here is this parenthesis here. That's going to be 1 over 1. M is the number of replicate measurements. The next guy here is going to be 1 over 3. That's the number, oops, H21 over 3. It's going to be 1 over 3. Come on, just shut up. And the last one here is going to have 2 terms. Have a numerator and a denominator. The numerator is going to be squared. And the numerator is going to comprise, got to get inside those parentheses up here. The numerator is going to comprise y unknown, which is this value, minus the average of the calibration points. So I'm just going to type average, right? And when I clicked on average to have it type average for me, it actually ate a parenthesis for me. So I need to add a parenthesis here. So I need to go back in here. Average is going to be over these guys. Right? Now in the denominator here, we've got m squared times, and this is called the dev square of x. And dev square is squared, so I'm not going to square that term. So let's see, dev squared. And again, that ate a right parenthesis. So I'm going to add a right parenthesis. I'm just going to sneak up on in there. Sometimes it throws an error when you do that, but Just ignore that error. Right? And this should do it. There we go, that 0.080, right? Now, one thing that's missing in this iteration is that the these guys should have F4. You know, if I don't want them to move, you know, when I pull the formula down. C5, I do want that one to move. So I'm just going to go F4 here, F4 here, and F4 here, and then F4 here, and F4 here. So that hopefully shouldn't change anything good. So now if I pull this one down, that will give the same value. So next we want to go from sample concentration to injected concentration, right? And to do that, we're going to use two named variables. It's MA1 and MA2. MA1 is the mass of the of specimen A here that we pipetted over, and MA2 is the total of the water plus that mass. So this is specimen mass plus water. And I'm going to justify that guy. And so what we have here is concentration times the ratio of the masses, MA2 divided by MA1, because we're basically going backwards. We've got the result from the instrument, now we're going backwards to the sample, right? So now lastly here, we've got to do the uncertainty in that undiluted specimen. So there's three terms here. There's SMA1 over MA1, SMA2 over MA2, and J5 over H5 is just the uncertainty in the sample concentration over the sample concentration. And so those three guys are root sum squared, so that the ratios are squared, and then we take the square root of the sum of them, and then multiply that by M5, which is the answer here. So this basically gives the relative error in the answer, and when you multiply the relative error in the answer by the answer, you get the error in the answer. So that's 0.822. Now we need to get to milligrams per can here, and that is just ppm in the can times the can volume. So milligrams per liter times liter equals milligrams per can. Milligrams per liter times liters per can, basically, is milligrams per can. And the uncertainty in that value is simply the uncertainty associated with parts per million in can times 0.355. So that's easy. And then the confidence interval, we're going to take T times S and divide by the square root of 3, right? So the T value there, the formula for that is T.INV 0.95 comma 1. 0.95 is the confidence interval, and 1 is the degrees of freedom. So T.INV 0.951 comes out to 6.31. And let's see here. So that is actually the CI here. Then the CI magnitude. The lower bound then is this minus this. The upper bound is this plus this, right? And then there's the nominal value, 45 milligrams per can. And we're going to ask the question here, Does 45 agree with 43.04 to 45.16? Yes, kind of just barely. You know? And then here is the next one gave the result 48.43 to 50.60, which is actually a little bit above the confidence interval. So without having a lot of accuracy built into this, accuracy assurance is built into this experiment, like spike recovery and method blank and internal standards, things like that. It's hard to say. But if these are accurate values, but this one agrees and this one doesn't. So that we don't really need to say too much about that for this report. Alrighty, guys. Thank you so much.